from the University of Zaragoza, Spain. So, Alberto, please.
Thank you very much, Sobin, and let me start by thanking the organizers for this invitation. It's always nice to get together with friends and share some mathematics, even though it's not the same as being there in Isfahan, and I remember very fondly my stay in Isfahan some years ago. But anyway, it's very nice to share this time with you. And I'm afraid I'm not going to talk about the representations of Lie superalgebras, probably about related topics, the second part of the title, just this. Yeah, I'm going to talk about some surprising ways to move from algebras to superalgebras that has appeared recently related with some symmetric tensor categories and the semi-simplification of these tensor categories. So fortunately, some of the definitions have already been given by Professor Yang. I will review a little bit that. But for me, things started with some non-associative triple systems called symplectic triple systems, which are related to the so-called Freudenthal triple systems, which in turn are related to Freudenthal's construction of the magic square, where the exceptional classic, the exceptional simple Lie algebras of type E4, E6, E7, and E8 appear in a unified way. And these symplectic triple systems appear every time you have a Lie algebra G over a field that contains a subalgebra isomorphic to SL2, so that as a module for this subalgebra, our Lie algebra G splits into the direct sum of the adjoint module, so the subalgebra SL2, and modules, trivial modules, a sum of trivial modules, this is our D, and then a sum of copies of the two-dimensional natural module. So we have a number of copies of the two-dimensional natural module. We have a number of copies of the trivial module. Well, that's the sum of the copies of the trivial module consists of just the centralizer of our subalgebra, SL2. So this is a subalgebra. The adjoint module and this bunch of copies of the two-dimensional module. And in this situation, the bracket in the Lie algebra can be expressed according to this splitting of the Lie algebra. And in particular, when one multiplies two elements in this odd part, because this gives a set to gradient. So if one gets the Lie bracket of two elements here, well, it has a part in SL2 and a part in the centralizer of SL2. And since the bracket is invariant under the axiom of SL2, one has to take into account the SL2 invariant maps from the two-dimensional natural module tensor with itself into SL2 and into the trivial module. So one has a precise description of the bracket in terms of a skew-symmetric bilinear form defined on this vector space T, and a symmetric bilinear map from T cross T into the centralizer D. And so every time we have a Lie algebra, it may be even infinite dimensional, with a subalgebra isomorphic to SL2 with this kind of splitting, we have a vector space T, which tell us how many copies of the natural module for SL2 appear in the decomposition. And in this vector space T, we have both a skew-symmetric bilinear form and a symmetric bilinear map into the centralizer of SL2. And then, well, these T's are called symplectic triple system. And see, at a certain point, I realized many years ago that in this situation, I can forget about SL2. I can just get rid of SL2 and get rid of the natural module for SL2 and just consider the vector space, which is the direct sum of the centralizer and the symplectic triple system. The centralizer is a subalgebra, it is the even part. And now we have a symmetric multiplication so that we take two elements in T and we get an element in D, which is given by this symmetric form that appeared, symmetric map that appeared before. And it turns out that in characteristic 3, if we play this trick of getting rid of this part and getting rid of this part, then what one gets is a Lie superalgebra. And this happens only in characteristic 3, only then. In this way, a whole new family of simple Lie superalgebras were discovered in characteristic 3. And essentially, many of the exceptional cases in characteristic 3 appear with this construction. So that was funny in a way and interesting, but restricted to characteristic 3. Later on, these new Lie superalgebras that appear over fields in characteristic 3 were also obtained with another construction in terms of so-called composition superalgebras. And we provide a construction of an extended Freudian magic square that included all exceptional Lie algebras, classical Lie algebras, E4, E6, E7, E8, and also a whole bunch of new simple Lie superalgebras that appear only in characteristic 3, are features of fields of characteristic 3. Okay, so this happened many years ago, and then quite recently, graduate student in MIT, Arun Kannan, a student of Ettinghoff, considered a completely different and surprising way of passing from Lie algebras to Lie superalgebras, mainly in characteristic 3, although he was able also to deal with some other exceptional situations in characteristic 5. And what he did, especially in characteristic 3, was he considered the exceptional simple Lie algebras, E6, E7, E8, E4. G2 doesn't work well in this case, but all the others do, and consider specific nilpotent derivations of degree 3. Okay. And once you have a Lie algebra with a nilpotent derivation of degree 3, and this is the case that I have in the original situation that I consider with the symplectic triple systems, because we can always take the joint action of a nilpotent element in SL2, and this gives a nilpotent derivation of order 3 in the whole Lie algebra G that we were considering. So this is related to the situation I presented before. So this nilpotent derivation allowed Arun Kannan to view the Lie algebra as a Lie algebra in the category of representations of the Frobenius kernel of the additive group scheme, G. So in particular, he viewed the Lie algebra as a Lie algebra in a specific nice category, nice tensor category. And he could use this because this category is not semi-simple, but one can semi-simplify this category. And in semi-simplifying this category, one gets the so-called Verlinde category in characteristic 3. And in characteristic 3, and this is the clue, this Verlinde category is equivalent to the category of vector superspaces. So Arun Kannan was able to get from a Lie algebra with a nilpotent derivation of degree 3 through this process of semi-simplification, he got a Lie algebra in the category of vector superspaces, but Lie algebras in the category of vector superspaces are just Lie superalgebras. So he obtained in this way all the Lie algebras that I had obtained previously in a different way, getting rid of SL2 and F squared, and using a unified way of doing things and a very general way. I should say, much more general than the way I presented it before. And this way, he was able to deal with all these new exceptional Lie superalgebras that had appeared in dimension 3 and 5, contra-gradient Lie superalgebras, finite dimensional. Everything here will be finite dimensional in the finite dimensional set. So I would like to show a little bit what's going on and how one can move from algebras to superalgebras, not only for Lie algebras to get Lie superalgebras, but for other varieties of non-associative algebras. I mean, not necessarily associative algebras. So this requires to review a little bit about symmetric tensor categories, but part of the work has already been done thanks to the nice talk by Professor Yang. I will review the process of semi-simplification of these symmetric tensor categories, and then I will give a recipe to go from algebras to superalgebras. I will not use nilpotent derivations of degree 3 as Arun Kanan did, but I will consider oromorphisms of order 3, which are nicer in the sense that whenever you have an oromorphism of order 3 in an algebra, immediately this provides an oromorphism of order 3 in, for instance, in the Lie algebra of derivations. And this is not valid for nilpotent derivations. So it's, in a sense, it's better to work in a setting which is a bit different from the one used by Arun Kanan, but the results are essentially the same. And you will see the recipe, which even if you know nothing about tensor categories or semi-simplification of tensor categories, by the end of the day, you can apply the recipe. If you have a nice algebra with a nice oromorphism of order 3, you can apply the recipe and get a superalgebra in the same variety. Okay, so this is nice. And just as an example, I will show you how to move from octonions to composition superalgebras. Because composition superalgebras only exist, composition superalgebras with non-trivial odd pair only exist essentially in characteristic 3. This is something characteristic of characteristic 3. And because Freudian's magic square was extended to, in a way that allowed us to discover some more exceptional contra-gradient simple Lie superalgebras in characteristic 3 using composition superalgebras. So one can use the semi-simplification of octonions to composition superalgebras to extend in a different way the classical Freudian magic square to the extended Freudian magic square. So symmetric tensor categories. Well, everything has been said already. Monoidal category is a category with a tensor product where there is a unit object and natural isomorphism, the unitors, so that tensoring with this unit object does essentially nothing. And there are natural, there is a natural associativity, which is given in terms of natural isomorphisms from X tensor Y tensor C into X tensor Y tensor C. And then there are some natural coherence conditions for unitors and associators, which correspond to this pentagon diagram and triangle diagram that Professor Yang showed. But these are the natural coherence conditions. A functor between monoidal categories is called a monoidal functor if it takes the unit object to, in one category, to unit object at isomorphism, and also if the functor behaves nicely with respect to the tensor product. And the way to express this is that there are natural isomorphism from f of x tensor f of y into f of x tensor y with natural coherence conditions with associators and unitors, I should say. So symmetric monoidal category, well, we need a braiding satisfying the natural compatibility conditions, this hexagon, this commuting hexagon that appeared in Professor Yang's talk, and also with the unitors. And the braiding is said to be symmetric if we have this property here. So the inverse of the braiding of x and y is the braiding of y and x. So in this situation, we get a representation of the symmetric group and these kind of things. So these are the symmetric monoidal categories. And then we need rigidity, and this means the existence of duals. So each time we have a dual, it means we have an object with an evaluation and a co-evaluation morphisms, taking into account the unit object, and with these compositions being the identity morphism. Well, in these compositions, I haven't written the associators. So Professor Yang took more care than me to write the whole sequence, including the associators and the unitors that are involved here. But I just got rid of them for simplicity. If you think of finite dimensional vector spaces, the evaluation is the natural evaluation. You take the usual dual vector space, and then we have evaluation of a linear form with a vector. The unit object is just the field. And the co-evaluation, you need to take dual bases, and the one goes to the sum of all the elements of the basis tensor with the corresponding element in the dual basis. And this is independent of the dual basis that you are taking. So these are quite natural things that happen for finite dimensional vector spaces. And finally, we need a tensor space, we need the braiding, symmetric braiding, we need the rigidity. And then a symmetric tensor category is a rigid symmetric monoidal category, which also is abelian and more than abelian category. It is F-linear. So the homomorphism between two objects is not just an abelian group, but a vector space over the ground field F. And the tensor product is bilinear. And we also require some finiteness conditions. So objects have finite length, and morphism spaces are finite dimensional. And finally, the unit object, the endomorphisms of the unit object consists of just the scalar multiples of the identity morphism. Since, see, all the endomorphisms, all the sets of endomorphism are not just sets, are not just abelian groups, are vector spaces. So in this case, it's just a one-dimensional vector space spanned by the identity morphism. And these are the symmetric tensor categories. So as examples, well, the category of finite dimensional vector spaces. This is the most natural one. The category of finite dimensional representations of a triangular Hopf algebra, or the category of finite dimensional representations of an affine group scheme. In particular, if you take constant affine group schemes, you can take the representations of a constant group, the corresponding category, or the category of finite dimensional vector superspaces. All these are examples with the usual tensor product and the usual braiding, which in the category of finite, in the first category is just the switch of the two elements, and the same in the category of finite dimensional representation. But for vector superspaces, one has to take some care with the braiding in this category. Okay, we need the notion of algebras in a symmetric tensor category. And well, an algebra is just well, for me, an algebra is not necessarily associative algebra. So an algebra is just a vector space with a bilinear multiplication. So an algebra in a symmetric tensor category is the same, an object with a morphism from A, tensor A into A. So if you take the symmetric tensor category of vector spaces, then you get the usual definition of non-associative algebra, not necessarily associative. So in this way, we can talk about commutative algebras in a symmetric tensor category if they behave nicely with respect to the braiding. So this is the condition. For finite dimensional vector spaces, the braiding is just the switch of the two components, so this means that the product is commutative. We can talk about associative algebras in any symmetric tensor category, Lie algebras, Jordan algebras, and well, things are a bit more difficult, and things work well if the identities that define the variety of algebras we are going to use are multilinear. So in principle, forget about characteristic 2 in the Jordan case. If the characteristic is not 2, then we can linearize the identities defining Jordan algebras, and then you can define Jordan algebras in a symmetric tensor category, and any other, you can do the same with any other variety of algebras. In particular, superalgebras are just algebras in the category of supervector space. So this is the setting in which things are working. Okay, the semi-simplification. And this is the interesting trick that will allow us to pass from algebras to superalgebras. Well, in symmetric tensor categories, we can talk about traces. So if we have an endomorphism of an object X, then in order to define the trace, we consider this composition. So first we consider the coevaluation, go to X tensor X star, then we apply endomorphism F in the first slot. Then we take the gradient, and finally we evaluate. All in all, we get an endomorphism of the unit object. But the endomorphisms of the unit object are just the scalar multiples of the identity morphism. So this is essentially a scalar. So scalar times the identity. So the trace is defined as this scalar that appears. And this is the trace. This is an endomorphism of the unit object, but this can be identified with the scalars. And then we can talk about the dimension. The dimension of an object is just the trace of the identity, the corresponding identity morphism. And with this, we can define the so-called negligible morphism. And F is said to be a negligible morphism if the trace of F composed with any other morphism in the reverse direction is always 0. Actually, you can put the composition of G and F or the composition of F and G and go in the reverse direction. It doesn't matter. The trace is commutative. Morphisms which are negligible are the subspace of negligible morphism is denoted by this n of xy, and this subspace is for a tensor area. This means that whenever we compose a negligible morphism by another morphism, we get negligible morphism. Whenever we sum negligible morphisms, we get negligible morphisms. And whenever we multiply with the tensor product a negligible morphism with another morphism, we get negligible morphism. And this allows us to define the semi-simplification of a symmetric tensor category. So we can obtain a new category, the semi-simplification, whose objects are exactly the same objects as in the previous category. But the vector space of morphisms consists of the quotient of the vector space of morphism in the original category, symmetric tensor category C, modulo the negligible endomorphism. So we get the same objects, but now the morphisms are morphisms in the original category modulo negligible morphism, modulo the class of negligible morphism. And this gives a new category, which is called the semi-simplification of our category. And then we have the natural functor, that is the identity on objects, and takes any morphism to the corresponding class, equivalence class of this morphism, modulo negligible morphism. And this is a nice functor that respects the gradient, the tensor products, and so on. The gradient in the semi-simple category is just the class of the gradient in the old category. Moreover, this semi-simple category is semi-simple in the sense that any object is a direct sum of finitely many simple objects, and the simple objects in the new category correspond to the indecomposable objects in the original category of non-zero dimension. What happens with the objects of dimension 0 is that they become the zero up to isomorphism, the zero object in the new category. And this is what happens. So many objects in the old category become trivial in the new category. In the composable objects in the old category now become simple objects. And now any object is a direct sum of simple objects in the new category, in the semi-simple category. Okay. So in particular, we can take a field of prime characteristic P and consider the category of finite dimensional representations of the cyclic group of order P, or if you want, of the associated constant group scheme. And this is a symmetric tensor category, and the semi-simple category that we obtain by semi-simplification is the so-called Verlinde category in characteristic P. And this Verlinde category in characteristic P greater than 3 has some interesting properties. It's a category that doesn't come from representations of any affine group scheme nor affine group super scheme. And because if we impose several restrictions on our symmetric tensor category, natural restriction then tends to be isomorphic to categories of representations, or either affine group schemes or group super schemes, but this category doesn't come in this way, cannot be presented in this way. This Verlinde category also appears as the semi-simplification of the representation of the Frobenius kernel. That's why what Arun Kanan did and what I'm going to talk about are relatively equivalent, but working with holomorphisms is nicer than working with nilpotent derivation. Okay. So now, what is the recipe to go from algebras to superalgebras? In characteristics, I will talk a little bit, just a little bit about other characteristics, but this is something that works well essentially in characteristic 3, and in a way it explains why in several varieties of algebras characteristic 3 presented some completely new objects that are specific of this characteristic and not others. This happens for Lie algebras, this happens from composition algebras, and so on. Okay, so we are going to consider the category of representation of the cyclic group of order 3 in characteristic 3. Okay, so we fix a generator, sigma, of our cyclic group of order 3. So sigma cube is the identity, and this means that sigma minus the identity, since the characteristic is 3, is nilpotent of order 3. Sigma minus the identity cube is 0. So we can consider when we deal with representation of the cyclic group of order 3, in a way we have to, we are dealing with vector spaces with a linear oromorphism of order 3, and this is equivalent to vector spaces with nilpotent endomorphism of degree 3, and we can look at Jordan blocks of this nilpotent endomorphism. And we have blocks of dimension 1, 2, or 3, and that's all that we can get. So this means that in the composable objects in this category are either of dimension 1, which is the trivial representation, or of dimension 2 or of dimension 3 with the natural actions, so sigma minus identity takes W0 to W1, W1 to W2, and W2 to 0. And then we have the corresponding action of sigma. So these are just the Jordan blocks that we teach to our linear algebra students. And then any object in this category decomposes as a direct sum of copies of V0, as a direct sum of copies of V1, a direct sum of copies of V2. It's just taking a Jordan decomposition, or taking the Jordan canonical form, if you wish, of oromorphism, a linear oromorphism sigma. Okay, now we semi-simplify. And when we consider the semi-simple category, this is the Verlinde category, in the composable objects V0 and V1 satisfy that the endomorphism in the new category are just the scalar multiples of the class modulo negligible endomorphisms of the identity. So in particular, in this category, these endomorphisms are spaces are one-dimensional. However, V2, any endomorphism of V2 is negligible. So modulo negligible endomorphisms, everything disappears. And there are no non-zero morphisms between different objects here. V0 and V1, V0 was simple, was the trivial representation. V1 was just indecomposable, but not simple. Well, now in the new category, in the semi-simple category, they are simple, while V2, well, all morphisms are negligible. In particular, the identity morphism has trace 0, so the dimension is 0, and this means that V2 is isomorphic to the 0 object in the new category. And this is a semi-simple category, and actually any object in this category is isomorphic to a direct sum of copies of these two simple objects, V0 and V1. And now, with respect to the tensor product, well, V0 acts as the unit object, and but V1 tensor V1 is no longer isomorphic to V0 plus V2. Well, it is isomorphic to V0 plus V2, but V2 is 0 now. So V1 tensor V1 is isomorphic to just V0 in the semi-simple category. And the braiding comes from the braiding. The braiding is obtained by considering the class of the original braiding modulo negligible morphisms. The braiding in the category of representation of C3 is just the usual swap. But then identifying V1 tensor V1 with V0 because they are isomorphic, the braiding here is minus the identity, while it corresponds to the usual swap in the other cases. So one has to be careful with V1. V0 behaves very nicely, so there's no problem about that. And then the interesting thing is that the Berlinde category is in characteristic 3 is equivalent to the category of vector superspaces, and the functor gives this equivalence, takes any super vector space to the direct sum of the even part and the odd part tensor with V1. And now the action of C3 is given trivially here, and the action is just the action of V1. So this is an object in the category of representation of C3, where the action of C3 is just in V1. And for morphisms, things go in the most natural way. And this is monoidal. This respects the tensor product. So we need these natural transformations. Well, these natural isomorphisms. These natural isomorphisms are the classes modulo negligible endomorphisms of this little j, which are given in this way. See, this is f of x, this is f of y, and this is f of x tensor y, up to here. So, okay, forget about technicalities. The only thing is that one has to take care of the odd part. This is the only thing, and then we have to add this lambda, which is a scalar, which is either 0 or 1. Okay. So this is, so we take symmetric tensors in V1 tensor V1 go to 0, and the skew symmetric tensors V0, well, V0 tensor V1 goes to 1, and then you apply skew symmetry. So these two categories are equivalent. And with this, if we have an algebra in our original category, then we can consider the corresponding algebra in the semi-simple category by taking the product modulo negligible endomorphisms. And then since the category, the Berlinde category is equivalent to the category of vector superspaces, it means that we have an algebra in the category of vector superspaces. So superalgebra with an even and odd part. So there is a unique superalgebra such that when we go through this functor f to the Berlinde category, we have something isomorphic to the algebra we started with in the Berlinde category. And in order to get this algebra, to construct this algebra A out of our original algebra, what we are going to do is, remember, any object in the category of representation of C3 decomposes as one-dimensional indecomposable objects, two-dimensional indecomposable objects and three-dimensional indecomposable objects, the copies of V0, copies of V1, and copies of V2. Well, this part gets trivial in the Berlinde category, the semi-simple part. And the two-dimensional parts, we can take all the Jordan blocks for sigma minus the identity and take the heads of the Jordan blocks. And with this, we form a subspace A1. So A0 is just a direct sum of copies of V0, and this part is just the direct sum of copies of V1 and A2 corresponding to V2, but this becomes trivial. And now here's the recipe. One works with all the definitions carefully and see. We have started with an algebra in this category. This means an algebra with an oromorphism sigma of order 3. So we start with this algebra. As an object, it splits in this way, as a vector space. So the multiplication that we have to define in this vector superspace is just the following. For even or odd elements, you just multiply in the original algebra, mu, you get this product, and then you project in the right part of the vector space. So the only problem is when we multiply odd elements. And then we have to multiply one of them times not the other, but the other with, we have to apply first the oromorphism of order 3 minus the identity to this second element. And then we multiply in the original algebra and project. So this is the only place which is not just the projection of the original product. We have to be careful. There is no problem in putting this sigma minus identity in the first component instead of the second. The result is exactly the same. The projection is the same. So that's it. This algebra, this superalgebra, because it is graded by the integers modulo 2, with this recipe to define the product, is the superalgebra that corresponds through this equivalence to the algebra in the Berlinde category. Okay. So if you know nothing about symmetric tensor categories or whatever, but you have an algebra in a nice variety over a field of characteristic 3, and you have a nice oromorphism of order 3, if you have these conditions, you can apply this recipe, define A0 bar and A1 bar as before, apply this recipe just blindly, and you get a superalgebra in the same variety. If you have started with a Jordan algebra, you get a Jordan superalgebra, and so on. You start with a Lie algebra, you end up with a Lie superalgebra. And just in characteristic greater than 3, one can, the Berlinde category is not isomorphic to the category, the semi-simple category, the semi-simplification of the category of representations, but this category contains a full subcategory which is equivalent. And Arun can use it also in characteristic 5 to obtain some, in particular, some nice simple Lie superalgebra that is specific of characteristic 5 and which is related to Katz's 10-dimensional Jordan superalgebra in characteristic 5. And in this way, everything. Well, let's see that I'm essentially out of time, but just, well, just as an example, composition algebras are algebras with a norm which is multiplicative. So the norm of the product is the product of the norms, and the norm is just a non-singular quadratic form. So these are the analogues with any field of real complex numbers, quaternions, octonions. The dimension is as you know, 1, 2, 4, or 8. And what happens is that in characteristic different from 2, we can linearize the definition of composition algebras and obtain composition algebras in any symmetric tensor category. One has just to define symmetry is easy. We start with a quadratic form. This means that we have a symmetric bilinear form. Well, in any category, we can think of symmetric bilinear forms, and the symmetry is in terms of the gradient. The multiplicativity can be expressed also in terms of the product, and the non-degeneracy of the bilinear form also comes using the rigidity of our symmetric monoidal category. So everything can be done in any symmetric tensor category, but what happens is the composition algebra, the unital composition algebras of dimension 8, the so-called Cayley algebras, have 4 different conjugacy classes of auromorphisms of order 3. And these were classified recently because they were needed, these auromorphisms, to define some idempotents in some other classes of algebras. So we knew all auromorphisms of order 3 in these algebras, and these appear in just 4 flavors: 1, 2, 3, and 4. The definitions are technical, but just appear in 4 flavors. And what happens is that for each one can think of the Cayley algebra as an algebra in the category of representation of C3 and take the same simplification and get the corresponding superalgebras. And in this way, one gets 2 different composition superalgebras, the B42 and B12, that appear for the first time in a paper by Sestakov, where he classified the prime alternative superalgebras, and they were shown to be unital composition superalgebras and to be the only ones unital composition algebras in a paper with Oku. So what happens is that one can semi-simplify Cayley algebras to get composition superalgebras. With Cayley algebras, one can construct the whole Freudian magic square. Then every time we have an order 3 auromorphism of a Cayley algebra, we can extend this auromorphism to the corresponding Lie algebras in Freudian magic square. And with this, one can extend Freudian magic square, which is something we did years ago, but in a different way, using a recipe to get the extended Freudian magic square with a lot of many other simple Lie superalgebras specific of characteristic 3. This is the paper by Cannon. This is the paper, the preprint where all of this appears. It's a joint work with my student Alberto Daza and postdoctoral student Umut Sajin. And thank you very much for your attention. I'm sorry for being so long.
Okay, thank you, Alberto. So is there any questions or comments? Maybe I have one question. About so in 2006, you proved the Lie algebra and the superalgebra structure can be constructed from both the orthogonal trip system and also the symplectic trip systems. So when the characteristic of the field, basic field, which is equal to 3. So in your result, this result also required the characteristics equal to 3. So why the characteristic equal to 3 is so important here?
Well, see, I should consider the situation in the reverse direction. And for years, we have been discovering some specific features in characteristic 3. Either for alternative algebras, only in characteristic 3 one gets simple or prime alternative superalgebras, which are non-trivial. In Lie algebras, when we move to Lie superalgebras, suddenly, even when dealing with contragradient, the simple contragradient finite dimensional Lie superalgebras in other characteristics essentially are the same as in characteristic 0. That's it. One has to be a bit careful. Sometimes SL3 is not simple in characteristic 3. One has to consider projective, special, linear algebra or superalgebra and so on. But then suddenly new examples appear. Some of them related to symplectic triple systems, some of them related to orthogonal triple systems, some of them related to other constructions. And see, now we know that what happens is that anytime we have an algebra over a field of characteristic 3, and we have an auromorphism of order 3, from that data, we can form a superalgebra in characteristic 3. And most of the times, this superalgebra in the variety of alternative algebras or Lie algebras has no counterpart in characteristic 0. or in other characteristics. So in a way, this explains why these things happen. Because in characteristic 3, when we semi-simplify these representations of C3, we get superalgebras in the same variety as before. And this is, for me, has been quite surprising. And yeah, but it's nice. There is a reason why only in characteristic 3, the semi-simplification gives the category of superspaces, and therefore we get superalgebras. In other characteristics, one can also, if you have an algebra over a field of characteristic 5 with an oromorphism of order 5, you can do the same thing, and you get an algebra in Verlinde category. And this is wide open. What kind of nice algebras are there? What are the simple algebras? So yeah, it opens many gates, all this.
Okay, thank you. So any more questions? Okay, if no, so let's thank Professor Alberto Elduque again.
Thank you very much.